Hey everybody, Dr. A here, and in this video we're going to be exploring another example of analyzing a system with 3D Cartesian vectors. So let's go ahead and get started. In the given information, we're being asked to compute the magnitude and coordinate direction angles of the resultant force. Now let's take a look at the diagram we have here. We've got our three-dimensional axes, right? So we've got a 3D vector system here. We've got the positive x-axis, the positive y-axis, and the positive z-axis shown here. But we're also showing a negative x-axis coming back here and a negative y-axis coming over here. So these black axes are showing some of the negatives in this particular example. Now the given force vectors that we have are F1, which has no x component, but it has a y component and a z component. So we have this 50J and 100K, but no x component, which really means that F1 is only in the two-dimensional YZ plane, okay? So it is not sweeping in an x direction. The x component is 0. Now, what about F2? Well, F2 has all three components engaged. It has an x component of 50, a y component of -90, and a z component of +80, and collectively both of these force vectors carry units of newtons. So as we start to analyze this, what I'm going to do is do a little bit of projecting for F2. Whenever we have all three dimensions engaged, like we do with F2, it's important to be able to visualize this really nicely, okay? So here's what I'm going to do. I'm going to take maybe the blue ink here, and I'm going to project F2 down to the XY plane. And we're going to show that it has an X and Y component like so. And if you remember from some of our background information, we can show that this is going to have a little shadow here, and we can call this F2 prime. Now, we're not necessarily going to use this directly, but again, this is just for illustrative purposes, just to help us see what's going on. And so I like doing this because now we can more clearly see that F2 has a negative x component, a positive x component, a negative y component, and a positive z component. Okay, so one more time, a positive x component, that's right here for F2, a negative y component, that's right here, and a positive z component, again for visualization purposes. Now let's go ahead and get started with the actual solution to what the problem is asking us to do. We want the magnitude and coordinate direction angles of the resultant force. So if we look back in our notes or our previous background videos, we know that a resultant force is going to be equal to the sum of the x components times I plus the sum of the y components times j plus the sum of the z components times k. And so because we have two forces, we can expand this out and say the resultant Cartesian vector is going to be F1x, let me draw that a little bit better for us, F1x plus F2x times I plus F1y plus F2y times j plus F1z plus F2z times k. So again, we're collecting the x components of the two vectors together, then we're going to collect the y components of the two vectors together, and then the z components of the two vectors together. And F1 and F2 are already given as Cartesian vectors. So when we write this out, we'll say FR is what? Well, we're going to have 50 plus, that is not right. We're going to have 0 plus 50I plus 50 minus 90j plus 100 plus 80k. And then all collectively, this is going to have units of newtons because each one of these components has units of newtons. So where did I get these values from? Well, this 0 right here represents that F1 has a 0x component, and then the plus 50 is the 50 on the x component of F2. And then when we go to the y component, this positive 50 is F1's 50j, and then this negative 90 is F2's j component or y component. And then when we go to the z component, we have F1 has a z component of 100 newtons, and F2 has a z component of 80 newtons. And so as a Cartesian vector, the resultant force comes out to be just 50I minus 40j plus 180k. And again, this entire resultant vector has units of newtons, and so each one of its components has units of newtons. So if we want the magnitude of it, which is what the problem asks for, we're going to say magnitude of the resultant force, and we're going to use the Pythagorean theorem, and we're going to use the Pythagorean theorem with 3 components, right? So we'll be able to say 50 newtons squared plus negative 40 newtons squared plus 180 newtons squared. And remember that negative here gets squared, so it becomes a positive. And so we're going to crank this through, and we should get 191 newtons. And so that's part of our answer, right? That's the magnitude of the resultant force, all right? Now, we also want the coordinate direction angles. Well, if you remember back from our previous videos or maybe in your notes, what are those coordinate direction angles? Well, we have cosine of alpha equals fx over the magnitude of the resultant force, okay? We'll call that frx, all right? And so if we want to crank this through, all we're going to say is that's 50 newtons divided by 191 newtons, okay? And we can do some rearranging, and we'll get alpha is the arc cosine of 50 newtons over 191 newtons. And when you punch that through, you should get 74.8 degrees, as long as you put your calculator in degree mode. Similarly, we're going to say cosine of beta is FRY over the magnitude of FR. And that's just going to be equal to negative 40 newtons over 191 newtons. And so we'll get that beta, not alpha, we're done with alpha. Beta is the arc cosine of negative 40 newtons over 191 newtons. Now, we need to keep that negative there. Keep that negative in the arc cosine operation and make sure that negative is included in your calculator calculation. And so when you crank this through in your calculator, including that negative, you'll get 102 degrees. And then last, we're going to have cosine of gamma equals FRZ over the magnitude of that resultant force, which is going to be just 180 newtons over 191 newtons. And so finally, we'll get gamma, doing some rearranging, taking the arc cosine, is 19.6 degrees. So that is really all of our answers, and we're really done now, but I want to wrap this up in a nice little figure, okay? I want to show what this total figure would look like, okay? So let's go ahead and use this as an opportunity to practice sketching our 3D vectors, okay? So we're going to draw out our axes here. Oh, that is not X, that is Y. And we're going to have the positive X-axis here. Let me redraw that a little nicer. Again, this takes practice, so it's okay if you don't, draw it perfectly just yet. So what is this resultant going to look like? Well, take a look back here. The Cartesian form of this has a positive x component, a negative y component, and a positive z component. So that Cartesian force vector is going to be doing something like this. Draw that a little bit better. Okay, just like that. And so if we were to try to imagine this, with some projection lines, all right, then, this would be projected down here, and we'll have this here, and then this is going to be projected over to the z-axis, okay? And so what are the components going to look like? Well, again, that x component was right here, all right? The y component is right here, negative in the negative direction, and then this is the z component here. So looking at this by components, this is 50 newtons, and this is, negative 40 newtons, or, it's actually more appropriate just to say 40 newtons because it's already pointing in the negative direction. And then we have 180 newtons here, and then the magnitude of FR is 191 newtons. And so that magnitude is the length of this 3D vector here. And again, I've got all my components here pointing in their appropriate directions. Notice that the 40 is pointing in the negative direction. What about my coordinate direction angles? Well, alpha is measured from where to where? Alpha is always measured from the positive x-axis to the vector itself. So this right here is alpha, okay? That's alpha. And then what about beta? Beta is always measured from the positive y-axis all the way over to the vector itself. So beta is this sweeping angle right here, all right? And then what about gamma? Gamma is measured from the positive z-axis, or the z component, to the vector itself. So gamma is going to be this angle right here, all right? And again, we know what those angles are. Alpha 74.8 degrees, beta 102 degrees, and gamma is 19.6 degrees. Another thing to notice is that you see that beta is greater than 90 degrees. It's 102. So that tells you that beta is swooping from the positive y-axis into this negative y direction, which supports the fact that we got a negative 40 for the y component. So this is just a good way to visualize all of this all together as a resultant force in 3 dimensions. So hopefully you found this video helpful. If you did, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.